evening. Today we'll look at how to do hypothesis testing or decision making for more than one sample. Two samples, but we'll also look at the situation where you have multiple samples. I think the situation is fairly clear. We have two populations, and now we take samples from each of these populations, and then we try to see if we can make some statements about statistical statements about the properties of these two populations. So we have two random samples now. They may be different sizes. We have two populations, and if in this situation here we know the variances, then and both populations are normal, or we can assume they're close to normal, or at least the central limit theorem applies. So this means that our sample sizes are large enough. Then we can use this statistic here, this Z statistic, to make a statement about the difference between the means of these two populations. Okay, so that's the first type of test. So the expected value of the difference between these two means is the difference between the expected values of the means. So it's mu1 minus mu2, and also we can look at the expected value of the variance. So and then we use the rules for making a difference between two random variables, and then we can get this here as the expected value of the variance of the difference of these two random variables, x1 bar and x2 bar. Okay, so this means that our Z statistic, if we think back on how we did for one sample, we just made a difference between the average of the first sample, the only sample we had at the time, and the value. Now we have both averages. We make a difference between those two, minus the difference between mu1 and mu2. So this is basically some difference that we assume, which is our null hypothesis, and then we divide through the square root of the two variances of the sampling distribution. Okay, and that has a standard normal distribution, and so then we can just apply the rules for the statistic based on the standard normal distribution. So how do we do the test? We have a null hypothesis, which is a certain difference that we want to see between those two populations, averages. The statistic we just defined, and so we can define alternative hypothesis, two-sided or one-sided, and then we basically look at the rejection criteria, and based on what the actual Z value is for the statistic, we can then make our decision. Okay, so that's not so very different as what we had for making decisions for one sample, so it goes fairly quickly. At the same time, very similar to what we had for the one sample case, we can also define a size. In this case, we have sample sizes equal, and we can define the size or the magnitude of the size, the value of the size, to have a certain power of our test. Okay, you remember our type 2 error, and the power being 1 minus a type 2 error. And so if we want the power of this to be large enough, we can then define or calculate what the n should be
to have a certain power to the test. So we can do this in a very similar way as what we've done last time. Okay, so just a calculation. So this theta here is the difference. Remember, when we have a type 2 error, we have to assume a certain difference between the values. And here, so this difference here is difference we put for the null hypothesis. This is the difference if the alternative hypothesis is true. Okay, and so this is how we then calculate this type 2 error, or rather the size to have a certain type 2 error. Okay, so I don't even have an example here, because it's basically just applying the 7-step procedure using this the test statistic that we just defined. What if we have variances unknown? Yes, welcome. We've just started. You've already missed a first test, I'm afraid. But,
because I can't enter this room by.
Oh yeah, the door is closed. There's still people outside.
Yeah, but I went to the door and I find out that I cannot go to this room, so I go to the side door.
And the side door was open.
Yeah.
Luckily. We'll check after the lecture if people have frozen to death outside. Yeah, we should keep the windows open.
All right, so the first test we've done, and you've missed, was when we
know what the variances are. So this is a situation which we typically don't actually have. So more typically that we don't know the variances. And then we have two cases. One case is where we can assume that although we don't know the variances, that they're equal. This is kind of strange, of course. We don't know them, but still we say they're equal. And we'll look later at the tests on how we can decide to take them equal or not equal. So this is maybe something to write down in your notes for your project. It's better to flip this around, to first do the test to see if you can assume that they're equal. First do the f-test, so to speak. We'll see the f-test later. And then you can choose the appropriate t-test. So if we can assume that they're equal, then what we do is something which is given here. We then make a pool of the data to estimate the sigma square. So we assume sigma 1 is equal to sigma 2 is equal to sigma. And so we calculate a pooled variance based on the variances we have of the two samples. Okay, you see how that works? And so we take the variance, what we have here is basically the sum of the difference between the measurement minus the average squared. You see that? Because our estimate of the variance is that sum divided by n minus 1, right? Maybe I should write it down, but I guess you know. So if we have a number of measurements, S1 would equal the sum of I going from 1 to half is n1. multiply that with n minus 1, so we basically just have the sum of that. And we do the same for the 2 sample, and then we divide by n1 plus n2 minus 2, y minus 2, and not minus 1. Yeah?
Is it squared? Yes, 1.
S1 squared, I'm sorry, yeah, absolutely. Yeah, thank you. Yeah, this is the variance. Yeah, thank you. So, yes, good that you are awake. Great. So, y divided by n1 plus n2 minus 2, and not minus 1, as we normally do, right? Yep.
Maybe
Combine both the minus 1 and 1 minus 1 plus 1.
You can look at it that way, yeah?
2 degrees of freedom.
2 degrees of freedom because of two averages. Okay, we lose, per average, we lose 1 degree of freedom. So we have the average for the sample 1, average for sample 2. So that helps. Okay. So and then with this pooled, so now we have an estimate of the variance for each of the populations, which is equal. So then we can define this test statistic T as we've done the Z statistic for 2 samples, but now we divide by SP over square root of 1 over n1 plus 1 over n2. And that follows from the rule we had earlier. So this sigma squared, we have to multiply with this factor here because of the variance rule that we have for the difference. Okay, if you go back to some lectures ago. So this is a t distribution. For the t distribution, we need to have a certain number of degrees of freedom that we calculate. Otherwise, we can't actually define t distribution. And there's a parameter of the t distribution is degrees of freedom. So in this case, n1 plus n2 minus 2, as we just said. And so this is an example. We have 2 catalysts. And we want to see how they affect the yield of a chemical process. We have this one catalyst which is currently in use. Catalyst 2 is acceptable, it is cheaper. And so we want to see how it changes the process yield and make our decision based on that difference. We run a pilot test and we show results. And we have the question, is there any difference between the mean yields? And we can assume equal variances in this case. So we have data which gives the yield of the process for catalyst 1, catalyst 2. We have the averages. For the 2 samples, we have the standard deviations, and we have the sample sizes. So we can then go to our 7-step procedure. Parameter of interest is the difference. We assume that this is 0, the difference. So our null hypothesis is 0. Alternative hypothesis is they're different. And so this is what we take as the statistic. We pool the variance. We have a pooled estimator here for the variance, but first we want to define the p-value. It has to be less than 0.05 to reject our null hypothesis. So we do the calculations. We know now how to calculate this pooled variance, which is 7.3. So calculating this through with our t0 value, we get minus 0.35. And now we have to go and look at the t-table, which is degrees of freedom 14. Why 14? 8 plus 8 minus 2 is 14. So we find that t 0.40 times 14 is 0.258. 0.25, 4 degrees of freedom 14 is 0.692, so our t0 is in between those two. So this means that our p-value is between 0.5 and 0.8. And how does that figure? So going back to our test statistics, so how do we get this 0.5 and 0.8? Does anybody know? I have looked at this example again. I'm now kind of surprised myself. Why is this 0.5 and 0.8? So we have a two-sided statistic, or a two-sided hypothesis. So we normally need to look at z alpha over 2, z alpha over 2. So this would be equal to 0.4 is alpha over 2, so that would mean this is 0.8 exactly, and this is 0.25 alpha over 2, so this is 0.5. Okay, it does make sense. So that's good. And so we see that p in any case is bigger than 0.05. So we cannot reject the null hypothesis, right? We have to have p lower than 0.05 to reject it. If you calculate through, p would be 0.73. In any case, much bigger than 0.05. So our decision would be what? Excuse me? If, are we going to use catalyst 2 or are we not going to use catalyst 2? We can use it, right? So it's cheaper and we don't have any evidence that it's different. Okay. So the second situation is where we cannot assume sigma 1 and sigma 2 to be equal. And then we use this test statistic. So you see it's slightly different. We don't have a pooled estimator, and also the degrees of freedom we have to calculate through this equation here. So it's a bit more calculation for the degrees of freedom. And so we then need to work with that system. So an example of that is given here. We have two situations in Arizona, Phoenix. Arizona is a large community, metropolitan community. And then we have rural Arizona, and we're looking at arsenic in drinking water. Okay? So arsenic is not healthy to have to ingest arsenic. I was recently pointed to the fact that rice has arsenic as well. Did you know this? Yeah, you know about this? Yeah, I was in shock. So, yes, the Belgian health organization has the recommendation not to eat too much rice. Twice a week is supposedly enough. This is traumatic, I assume, for Chinese people who eat rice morning, noon, and evening. So, and they don't, yeah, when I talk to Japanese and Chinese people, typically they don't know. How do you know?
For arsenic?
Yeah.
What do you mean? How do I know?
How do you know that there's arsenic in the rice?
You can measure them.
You measure it, okay. How do you measure it?
And digest this acid.
digest with acid and then you measure it.
Yeah.
Have you done that?
Yeah.
You measured it?
Yeah, I measured it.
Ah, right. Which rice did you take?
Different kinds of rice.
Okay.
Yeah.
That's amazing. All right. Can you send me the result, please? Or is it something you want to publish? You want to publish it, all right? It's a secret. All right. So, but can you tell me which rice we're supposed to eat to have less arsenic? Because this is an important question.
It also depends how you cook it. When you dry or you use weight method or dry.
A dry cooking method for rice, how does that work? You use less water.
What is the optimal method for?
Yeah, I've been told you have to put additional water and then pour away the water. Okay. So this is very important. Thank you. So when you do publish your results, please send me a comment.
We all need a copy, I guess.
We all need a copy, yes. But people have already done the research on this, right?
Yeah.
Yeah.
And also arsenic in soil because you plant the rice in soil.
Yeah.
So,
Yeah, but it seems to concentrate in the rice plant. The arsenic, it seems.
I think there is already some paper.
Yeah. Yes, okay. So, but in this case, it's not in rice, it's in drinking water. Anyway, so, but thank you for this health update. So, you see the values which are found in certain communities in the Phoenix area, and this is in rural Arizona. And so the question now is, if we're going to be drinking water, should we take it from Phoenix or from rural Arizona? If we have the choice, is there a difference? If you look at the probability plots of these two situations, you see that the slopes are very different. So this is an indication that we have, so this could be a way to check if you have different variances for the two populations. Okay? So different slopes. So you can kind of assume that in this case we don't have the same variance. And so we use the other method, the one for variances different. Okay, so this is then our test statistic. This is our calculation for the degrees of freedom. You see that we go from 13.2 here. If we put in all the values, we go from 13.2 to 13. So we round down to the nearest integer. And then we can calculate what our test statistic is for the situation we have. And then we compare with the t distribution for 13 degrees of freedom. And you see that for 0.01 we have 2.65 for 0.005. So our value is between these two. We had as alternative hypothesis that they are different. So this means that we have to, you would think that you would have to also multiply this by 2. Which isn't done here, okay? So this could be an error in the book then, I would say. Unless I'm not thinking straight. So we have to, because this is alpha, normally if you have a 2 sign, this is alpha over 2, right? So if you want to find the p value, so we should multiply, if you want to find alpha, we should multiply with 2. So it should be 0.02 to, no, I'm not thinking straight here. This 0.01 is coming from this one here, and this is 0.02 coming from there. Okay. You had seen that, of course. Good. So it is right what is here, and so we reject in this case the null hypothesis because our p-value is less than 0.05. And so what does it mean? It means that there is a difference in arsenic concentration and it seems to be higher in Arizona, rural Arizona communities. Okay. All right, so this is how that works. So these t-tests for variances known and variances unknown. All right. So this is just the same information. We plot this once again. All right. So you remember that we could also do a type 2 error for a situation where we do not know the variance. These operations or operating characteristic curves, as they're called, we looked at them last time. So we can do exactly the same here, and we have to take then for the d value on those OC curves, we have to take this as a d value, and then we can do the same. We have to do this we can only do this for the case where the variances are or can be considered to be equal. Then we can do it. And where the sample sizes are the same as well. So, okay. We don't have an example here, but I think with those prescriptions you could find an appropriate sample size to have a certain power to your test. Okay, so let's talk about this paired t-test. This is a special situation where you have two samples, but you have information in the testing that allows you to look at the data set in pairs. So we have a pair of observations. So this is sometimes very obvious that this is what needs to be done. So an example, let's maybe look at the example first. So we have steel plate girders, beams basically. And we have several methods to look at the shear strength of these construction elements. And we have two methods. We want to compare the Karlsruhe and Lehigh procedures. So two procedures probably thought out by research teams in Lehigh and Karlsruhe, Germans and Americans. And so we want to compare the two methods. Okay? So we have different beams, girders, that we test with both methods. And so we now want to see if there is something which is different between these two measurement procedures. And so we can look at each of these or these two measurements as being paired, because it's the same girder we're testing now with two methods. Okay? And so it's obvious that we want to pair these two and look at the difference between those two and then compare these differences, or have as our measurement sample. The sample would then not be each measurement, but just the differences. Okay? So this is basically what is being said here. So what do we do then? Instead of having now two samples, basically we have just one sample. So we go back to the situation where we just have one sample. We combine our two samples to one. And so our test statistic or our test situation, null hypothesis, is that the average of the sample is a certain value. It could be 0 or some other value. And then our test statistic is back to where we were for the single sample test statistic. And so we have our average for the sample minus this value, and we divide this through with SD being the standard deviation on the difference, the sample of differences divided by square root of n being the sample size. Okay, and so we can do basically just the same t-test, but now for this paired data set. Okay, so very easy to apply that. Who wants to run through this? Just for me to be able to admire the way you do that. All of us? You've done it already, haven't you? No, you haven't been able to use this machine? Okay, there you go. That didn't work.
So we have the parameter of interest, which is the difference in mean shear strength between the two methods. So the null hypothesis would be the difference between those is equal to 0, and the alternative would be this is not.
So it's a two-sided alternative hypothesis. Yeah.
And this is the test statistic.
Right.
So the assumption is we reject the null hypothesis if the p-value is less than 0.05. Yeah, these are the test statistics calculation. From the calculation, we conclude that the test statistics exceeds the t value. So we conclude that the two methods have different yield results.
Yeah, this t value, you see it's 0.0005. Yes, 0.0005. Comma 8. So the degrees of freedom is 8. Does that make sense to you? Why it's 8? So if you go back to our data set. So when we started out, how many?
We have 9 and
9 minus 1. Yeah. So if we wouldn't pair this, we would just compare these. So the alternative to this paired t-test would be to have a two-sample t-test, right? So we would have to then look at the variances of these two and decide if we take the one for equal variance or the one for different variance, right? So if you take the one for equal variance, what would be our degrees of freedom? 16, right? So we now lose degrees of freedom by doing this paired t-test. So when we lose degrees of freedom, this means that our t-test, our t-distribution becomes wider. So in a certain sense, we're losing information, so to speak. So to do a paired t-test only makes sense if you really have this pairing of data. Because what are you doing? You're comparing things which are should be similar. Okay? And so you're looking at the differences of something that should be similar, and so you use that information to make a new data set. So the information in the data set is now of a higher quality, right? But you lose resolution on the test because you lose degrees of freedom. So this is a choice you have to make. And typically it makes sense to go to a paired t-test So this is this paired versus unpaired comparisons. It makes sense to go to a paired t-test if you have this link between the data sets. So then the quality of your data set, the information quality of your data set is going up. And this should normally compensate for the loss in degrees of freedom. Okay? All right, so it says this here. Let's see if I now understand this myself. And if you understand it, the experimental units are relatively homogeneous, small sigma, and the correlation with pairs is small. The gain in precision attributable to pairing will be offset by the loss of degrees of freedom. So an independent sample experiment should be used. Okay, does this make sense to you? So what does it say? So if the two data sets themselves are fairly homogeneous, meaning they have a small sigma, so we don't have very big spread on our data. And the correlation in pairs is small, so we don't have actually a very good connection between pairs. And let's look at our data set here. So this is 1.186. So here the difference is, okay, so you see if we go from here to there, what's the biggest, what's the smallest number here? This is the smallest number, right? And what is the biggest one? The last one. Okay, so we have something which goes from 150 to 550, so it's 0.4. And here we have something which goes from 0.99 to yeah, so it's something like 18. Yeah, so 0.18, so here 0.4. So obviously there's much more spread here than there. Right, but you see the difference between those two seems to be smaller than the difference you have in this series. Okay, so if you go there, this is something like less than 0.2, less than 0.2, this is 0.3, almost 0.3. So, but still, you see that these are closer together, it seems, than what we have in this series. So there, and they should be if one goes up, the other one should also go up. So there should be some type of correlation. So we could actually draw the correlation as well between those two. Okay, so basically what we're saying is that if this is a data set which is fairly heterogeneous, the heterogeneity may be coming from the samples, right? Not from the method. And so the heterogeneity coming from the samples we can remove by taking the difference in pairs. All right? So I don't know if this makes any sense to you. I know I was struggling with this when I was your age, when to take a paired t-test or not. So these are some clues on how to see when to take a paired t-test. It also just makes sense here, of course, we have two measurement methods which we want to compare. So if we have the same sample and we compare with two tests, they should be in some way, hopefully, correlated. Okay, we can also do then a confidence interval on this exactly the same way as we've done this before, so I don't want to emphasize this, and we'll just skip this example. All right, so let's look at a different situation or a different type of test, the F distribution, where we have the question on the variance. So now we're not comparing means, we're comparing variances in two populations. And so the null hypothesis is that they're equal. The alternative hypothesis is that they're different. So this is the test that we want to do before we do the t-test on two samples, because this actually helps us to decide which t-test to do. Okay, so typically people in the project do first the t-test, and then they do the f-test. And sometimes that result of the f-test is not consistent with the t-test they've chosen. So that's a bit sad when it happens. And most people catch it on the exam because they've studied the thing, but while they're writing the report, they may not be in tune with us. So if you write it down somewhere now with some type of exclamation mark. Have you done that? No, you haven't done it yet? To draw your attention, maybe you have a special page in your book where you have all the tips I give you for making a perfect report. You have this page somewhere in your notes already? Have you made this page? Not yet. Okay. But you're going to do that now. Good. So we have the F distribution, which helps us to make a decision. Namely, do we decide that the variances are equal, or do we decide that they're different? So how does this F distribution work? We have W and Y independent chi-square random variables. So you remember chi-square, the chi-square distribution, which we had last lecture, and we have degrees of freedom U and V. So if we make then the ratio of W over U and Y over V, that is then an F distribution, and this is the function which describes the probability density function as we have these two parameters U and V. All right, so this F distribution then has three parameters, you could say, or the value which we will look for has three parameters. This is the alpha, the significance level, V and U. Okay, and if we look at F1 minus alpha, U and V, this is this portion of the integral, and this is the area F alpha U V. And you see that we can use this because this is tabulated. If you want to calculate this here, we can find this by using this equation. And you have to notice that U and V are switched here. Okay? So this is a little trick which you can use to calculate this F1 minus alpha UV. Okay, so if we now have two random samples from two normal distributions with different mu's and different sigmas, then we can also say that the ratio of the S1 squared over sigma 1 squared is a chi-square random variable. This is also a chi-square random variable. So this ratio should then also be F distributed with these degrees of freedom for the numerator. The numerator is the top of the ratio, and the denominator is the bottom of the ratio. Okay. And so if we have as null hypothesis that sigma 1 equals sigma 2, our test statistic then becomes this, because we can basically remove sigma 1 and sigma 2 because we assume them to be equal. So under the null hypothesis, our test statistic then becomes this. Okay, so it's fairly simple then. We can just take the ratio of the variance of sample 1 over the variance of sample 2 and look at our rejection criterion. We look for the F value for a certain level of significance that we are aiming for. And we have our 2 degrees of freedom, which we are looking at, or we find from our sample 1 and our sample 2. We find this back in, of course, -1, because once again we have lost 1 degree of freedom by taking the average. Okay, so our test procedure, we can have one-sided or two-sided. And so let's see how we apply this. This is an application in semiconductor fabrication. So we have oxide layers and we want to etch them. And we want a certain thickness, and we etch by exposing them to a mixture of gases. And now the variability of the thickness is a critical characteristic of the wafer, and a low variability is desirable. Okay, we now have 2 different mixtures of gases. And we want to know if one is better than the other. We have 16 wafers are etched in each gas, and the sample standard deviation of oxide thickness is S1 for the first mixture, S2 for the second mixture. And this is given in angstroms. So is there any evidence to indicate that one of these gases is better than the other? So we want to look at this null hypothesis that they're equal, alternative two-sided. And so our test statistic is then just the ratio of the variances, and we have degrees of freedom equal to 15. And so if we look at alpha equal to 0.05, two-sided, so we are looking then at F equal to 0.025, 15, 15. This is a not so interesting example because we have the same sample sizes. So say we would have 20 samples for S1 and 15 for S2. This would then be equal to 19 and 14, right? So this is the one from the top, and this is the one from the bottom. Okay, and the other one is this one here. This is 1 minus alpha over 2 and 2 degrees of freedom, and we can calculate that by doing 1 over F for 0.025. You remember our rule or equation that we can use, 15, 15. So this 15, the left 15 is coming from the right 15, and the right 15 is coming from the left 15. So this is so you have to make sure that you get that right. And so then we can calculate this F0 and compare it to these two values. We can find the F values, critical F values in the tables, which are in the back of the book. And so we find 0.85 for our situation. We see that F 0.975, 15, 15 is 0.35, and this is 2.86 for this one. So we are in between those two. So this means we cannot reject the null hypothesis. So we can assume that they're equal. Well, okay. So we have no reason to reject the null hypothesis. All right. So if we would do this, if we now would do a t-test on the averages, we would take the t-test for variances equal. Okay? Because we have no indication that they're different. And this is our F table. So 15, 15 should be here, 2.86. And so this is our 2.86, which we find here. So that seems to be correct. All right. We can also do a confidence interval. You have to also here be careful how you do it, and that you have you're using the correct degrees of freedom in the correct places. So when you apply this, just make sure that you do it correctly. And to come to this equation, the explanation is given here. This is something you can easily check for yourself. But this is how to do it. So this is how to calculate the confidence interval on a ratio of variances. And I think we also have an example of that. And I will let you, or maybe we'll do it together anyway. Who wants to give it a try? Shall I give it a try? We have impellers in jet turbine engines. We want a certain surface finish. Two grinding processes are being used, and manufacturing engineer would like to select a process with the least variability of surface roughness. So we have 11 parts, and this is the standard deviation, and then a second random sample for the second process, 16 parts. This is the standard deviation of that series of measurements. And so we want to find a 90% confidence interval on the ratio of these two variances. So we just do that in calculation. This is S1 squared over S2 squared. We fill in the numbers. We find this F0.95, 1510. Why 1510? This was 16, this was 11, so our 2 degrees of freedom are 15 rather, 10. And so we need to go back here, and this is 2, so we have to have 15 here and 10 there. Okay? So it's because this is flipped over here, this also flips over, so this is slightly confusing. So you have to keep your widths about to make this correctly. So we have 15 coming from the 2 here and 10 from the 1 there. Okay, this is the same thing on this side. 15 from here, 10 from there. And so this then, if we fill out the numbers, 2.85 it should be for 1510. Let's check. 15U is the top one. V is the the vertical one. So U is the horizontal one. So we should go 15 here and 10 there. So you can see, oops, 3.52 we have now. This is interesting. And we had here. Okay, so what did we do wrong? Degrees of freedom. Aha! We're looking at the wrong table. This is F0.025, so we have to look at F0.05. Okay, so this is something to keep in mind as well. We don't have a table, so you should check on the table who has the table in front of our turn. Could you bring can you check if we have 2.85 or F.05?
What's the value?
What is the value?
The value is 2.85.
Yes, it's right.
It's right? Thank you, Faye. This is very good. So this is right. And this we find by taking this 1 over 2.85 to be here. So why do we take 0.05 here? Why not 0.025? Because we have a 90% level of confidence. So alpha is 0.1, right? 10%. So then we have to go two-sided, we have to go to 0.05. Okay. So this was interesting exercise anyway. All right. So this is a good time to have a little break. If I look at you. If I continue, this will become dangerous for me, I think.